I have three things to present, which give, I think, a nice story. The first one is correlations between two individual atoms. It looks a little bit like an interference pattern, but it's not. The second one here is correlations between three, in this case, three itinerant fermionic atoms that form what has been named a Pauli crystal. And the third part of the talk, I think most of the audience hasn't seen yet, that is two-particle correlations in a mesoscopic system, and we think by now that we can call this somehow an observation of Cooper pairs. Okay, in the town of Copernica, I thought I should somehow go back to the roots of quantum optics and somehow start with something astronomical. Yeah. So, and the Hanbury-Pound-Twiss idea that has been already mentioned now in several of the talks here actually originated from astronomers' observations. Yeah, and people used. So did I do this again? No, it doesn't want to work. Okay, people used radio frequency antennas spaced by a particular distance and interfered the signals, which of course in the radio frequency domain, it's really just interfering electrical signals on some power recorder, and they call this microscopy interferometer, to measure the extent of radioactive objects. Yeah, and it was Hanbury, Brown, and Twiss who realized that what they could also do is, instead of interfering the amplitudes, actually measuring the intensities of the individual receivers, and actually just measure correlations between the intensities, which is a big advantage if you want to put these detectors very far away, such that doing actual amplitude correlations would be a very challenging task. Okay, and then of course you will immediately ask the question, can you also do this not only with radio waves but with light? Yeah, and they actually also did that. And here is already their first setup, which they did actually then in the laboratory to mock the system they actually wanted to use then to observe, to do in astronomy. And that's really already the setup that we nicely draw to actually measure G2 correlations of light, after all. Yeah, correlate to photon detectors after a beam splitter, and then usually changing the delay in time. So what they did, yeah, after this successful experiment, they actually went and did astronomical observations. This is, I have to redo it here, two telescopes of which they can change the distance between, and they observed correlations of photons coming from our closest star, Sirius, and their paper had just 4 data points here, which is consistent in fact the decay of correlations as they move these detectors further apart with some millirads of apparent angular, milli arc seconds of apparent size of the star, which is pretty good in agreement with also today's observations of how big Sirius actually is. Okay, so this is just then a question, is this something like interference now between different photons? And there is like a wording from Dirac, which is which has been debated then a lot. Each photon then only interferes with itself. Interference between two different photons can never occur. And he actually added this word "different" in 1958, even after observation of this. Yeah. Now, this is rightfully discussed and questioned, this statement. And I think to clarify this, there's a very pedagogical experiment done by Hong and Mandel, which of course all the senior people in this audience have been discussing many times, and I still like it a lot. Yeah, so you have two indistinguishable photons coming in on a beam splitter here, depicted by the black lines. And of course, now I'm using different colors, but they're indistinguishable. And you can see there's 4 different ways how these two photons can pass these beam splitters. They can go out like this, they can come out in two different ways on the same side of the beam splitter, or they can come out in this way. Yeah? And now what you can see here is you actually have to consider an interference of different amplitudes of a certain state, quantum state, and two of these three possibilities interfere destructively because we're dealing with indistinguishable bosons, which have to be symmetrized with respect to exchange of them, and that's how the two photons have to come out at either port of the experiment. So that is, I think, one of a very stunning experiment to understand this kind of subject. And you can immediately ask the question, can I do this with many more photons? It could be very interesting. Yeah, and that is being done. But it gets tough if you add more and more photons because you have to have many, many photons being observed at the same time. You know? It's a little bit easier with massive particles, and I will show you in the course of this talk how we are doing this. So first of all, I give a very short note how we've been preparing individual atoms in a very controlled setting, basically in a discrete quantum state. Yeah? And how this works is we are using fermions, and if you take a Fermi-degenerate gas, as has been the subject of many of the talks in this conference already, then if I look in momentum space, in the center of the Fermi sphere, there's basically unity occupation of every possible cell in phase space, but then really excitations live at the edge of the Fermi sphere. There's some holes and particles, and so the basic idea is really just cut off the Fermi sphere and have like only singly occupied sites left. Yeah, and of course the idea is simple, but the task is not quite so simple. So how do we do this in the experiments? We fill a degenerate gas in a trap, and now we have to make sure we control the number of bound states in this trap very well. And we do this by tilting the potential using a magnetic field gradient. And in this way, if you do this well, then the number of bound states can be very well determined, and we can even bring it to exactly one single bound state left in the trap. And then having, depending on what we exactly do, one spin up, one spin down, or just a single spin, just as we wish in our systems. Okay, what does the experiment look like? I won't bother you too much with details. It looks complicated, yeah. But the major ingredient is a tightly focused dimple beam, just as also Florian had it, from some high numerical aperture lens. And we can also use some spatial light modulator to actually adjust, for example, the size of that beam. Yeah? Then what we can also do is we can use an acousto-optic deflector to actually create simultaneously several ones of these little dimples. Yeah? And we can now prepare individual samples in each of these dimples. Yeah? For example, and that's the first experiments I'm going to show, we can prepare one atom in each of the two dimples that you see here. Okay? And so that's the experiment. We prepare one atom each. Then we let this, now what we are interested in is correlations between the two. Yeah? And so in principle now, these two atoms that we are having, they're sitting in two independent dimples and they can't see each other. They don't know of each other, okay? They don't know of each other, but now we want to see, are there any correlations between them? And one idea is to just look in momentum space, yeah? So what would you see in momentum space? If I just switch off simply the dimple, then this particle will just fly and move, and we will just observe the momentum after some time of flight, yeah? And now, of course, we are interested in the line of sight between the two dimples, huh? And that's why what we do, we use some kind of optical waveguide along this direction in which we let the atoms move. And then after some time, we record their positions in some way that I'm also explaining very shortly. We use some fluorescent light that we let go on the atoms. And because we are very efficient in collecting the individual fluorescent atoms, we can collect enough photons from one atom before they have moved too much. Yeah? And so that's how we obtain the positions of the atoms after some time of flight, giving the momenta of the particles. Okay? So that's what such an image looks like here. And now what we plot, like we do this experiment many, many times. And then we obtain two momenta of particle 1, particle 2. They're obviously indistinguishable. So these axes are actually then now exchangeable, but from one shot, we get exactly now one position, one point in a two-dimensional space here. This is position, a momentum of particle 1, momentum of particle 2, okay? And now we can get a histogram. We just plot all the shots that we take, and it looks like that. So it looks like an interference pattern, but it's actually something a little bit more complex. It's some correlation function correlating the momentum of particle 1 and 2. Yeah? If I were to look at only one particle, its density would just be the Fourier transform of the wave function inside an individual well. Okay? But now, because even though these particles, they don't see each other, they're non-interacting. Yeah? After some time of flight, you will actually find that their positions are correlated to each other. Yeah? For example, you will never find two particles, both particles having exactly the same momentum. Yeah? And that is then, of course, due to the fact that these particles are fermions. Their wave function with respect to exchange of the two particles has to be antisymmetric, and so they can't have the same momentum. Yeah? You can now take the integral along this diagonal direction, giving you basically taking out the center of mass of the system, and then you can actually look at this interference fringes, and the contrast actually in this case is consistent with how precisely the two particles are indistinguishable in our experiments, because this waveguide that we are applying, it's not perfectly aligned with the dimples. So because we are dropping them somehow in the waveguide, it's not perfectly in the center. There's actually some way of knowing a little bit, getting a little bit information of where each of the two atoms came from. Yeah? And that gives us the finite contrast here. Okay, that's two particles. Can we extend this to more? Yes, we can, but I don't want to go in too much detail. It gets a little bit more complex to plot, because now to just get a plot like this one, we would now need 3 coordinates, but we can immediately integrate out what we did here. Just integrate out one coordinate, we get a pattern like that, and we can also understand how it comes about. Yeah? So there will be 3 particles. And you can very clearly see, if you want to do this with more particles, it gets tedious, and we don't know exactly how to analyze. And these are still, I should say, non-interacting particles, so the physics is in many ways very similar to what happens with photons, just that these particles are now fermions, so they are anti-symmetric with respect to exchange. So then, but there's one setting that was actually pioneered here. There was some proposal from Marius Geider's group to look at correlations between more particles and actually visualize them. So here we jump now to a slightly different setting. We use now, instead of 2 individual dimples, we use 1, and we can make it a little bit larger using a spatial light modulator, and we use some additional interfering laser beams from the sides, which gives us a lattice in the vertical direction. And now what we do is we load all our atoms into a single plane of this vertical optical lattice, such that our trap is now an oblate, has now an oblate shape. Okay? So it's kind of a quasi 2-dimensional setting. And now we do this, we prepare now our particles, not in this very tightly focused dimple, but in this 2-dimensional geometry. And as we lower the trap depth, we observe how many particles are remaining in the trap. And now what we see is, as we lower the trap depth, there's a step at about 12 atoms. There's another step at 6 atoms, and a third step at 2 atoms. Well, where does this come from? And actually, okay, you can see for every of these plateaus, the fluctuation in atom number that we observe is kind of minimized. Yeah? So where does this come from? Because now we have a 2-dimensional setting, and I should say we can approximate this roughly by a harmonic potential. Now they're degenerates in the system, because I mean there can be excitations in both 2-dimensional directions. Yeah. So the first level is of course not degenerate. The second one is 2-fold, and the third one is 3-fold degenerate. And now as we lower the trap depth, we can basically cut away particles from at higher and higher energies, and this creates now these steps. By now we can also do 20 particles. Okay, so that's how we prepare the system. And now what we do is we do experiments only with one of the spin states, and the system is still non-interacting. Okay, so and we still look at momentum space. So what we do is we let the atoms now expand in a sheet, and an image looks, for example, like that. That's the momentum of, in this case, 6 particles. Okay, and now here comes now the intriguing thing. How can we analyze this data? It looks like maybe it has a little bit of structure. If you look at many shots, it looks like this. In some of the shots, you might think, I can see structure. In others, I can't. Yeah. But there was this ingenious idea how you can actually reveal correlations out of this. Yeah. The idea is the following: you see something, some orientation. You can first of all remove from all the images a center of mass motion, because I mean that doesn't matter. It's just some uncertainty that you add. So you subtract that, and then you orient all the images that they are most closely related to each other. Yeah. And then what you obtain, for example, for the system of 6 particles is something like this flower. It's maybe not quite as beautiful as Francesca's flower. It has only one, also one atom less. I think she had 7, right? 6 around and 1 in the center. Okay, but that's what it looks like for 6 indistinguishable fermions. There's no interactions there which produce now this spatial order that is now made visible in this way. Yeah, there's also a very nice way of visualizing this in some viewpoint that Christy Chu wrote on the paper. Basically, you have these individual images which somehow look like this, and then you orient all these images, because I mean the system is rotationally symmetric. Yeah, so you have to find somehow a way how to break this rotational symmetry, and that's how you have to rotate each individual image to produce then the final pattern. Yeah, so we can do this also for 3 particles, and more recently Sandra, who is in the audience, did this for 10 particles. So it works, you know, by you can increase a little bit the particle number, but then it gets, you can already see it gets a little bit more and more washed out. So this is really in the end these Pauli crystals is like in the end somehow a few body effect, if you want, but a very interesting one. Yeah, and of course what we are looking for now, this is now non-interacting particles. Can we find, I mean, if anyone has some ideas how to find techniques to visualize many particle correlations also for more complex settings, that's what we are very interested in. Yeah? And we are starting already to explore. Now, this was all non-interacting systems. Now we are trying to do similar things, but we try to do this with interactions. And for interactions to be there, for our contact interacting lithium atoms, we have to now put in 2 different spin states. So there's a mix of 2 different spin states. And if you want to measure then their momenta, we have to quickly switch off the interactions, which we do with some spin flips. And then we again do the same thing. We let them expand in time of flight, and we measure their momenta. Okay? And now one of the crucial things is, of course, that we have to take an image of 1 spin state, and a very short time afterwards, such that atoms don't have time to move, we have to take the next image of a 2nd spin state. Okay, and we can combine these 2 images to 1, and now we have here a completely spin-resolved momentum distribution of in total 12 particles. Okay, that's what you see there. And now the question is, what can we do from this? I mean, do you see any structure in this? We can look more carefully, and we can look at many shots. Yeah, what we would like to maybe see is that some pairs occur. Yeah? And if we're talking about a Fermi gas, the typical thing is inside the Fermi sphere, there's no way for the particles to adjust to optimize their energy, because all the phase space is filled with other fermions. So the only way how they can optimize their energy is to form pairs on the Fermi surface. Okay, so we would like to see something like that. Yeah? That on the Fermi surface, 2 particles form, and if I have a particle at a spin with a spin up at a certain momentum k, then there should be a particle with momentum minus k on the other side. Okay, let's try to analyze the images. So that's basically we have to do some second order correlations, evaluate some second order correlations. So this kind of a quantity. And what we do is to get some visualization, we fix the position of a down particle. Basically, we select all the images where the spin down particle has a certain momentum. And then we plot the histogram of where all the up particles are. Okay? And that's what this basically looks like. We fix the spin down particle, for example, here. Of course, we can all rotate all the images because, I mean, there's no, there is a kind of cylindrical symmetry. And then plot the density, and you can see there's basically noise, yeah, within a certain range. And there is some circle up to which there we see observed noise, and that's basically the Fermi surface. That's where the density of the cloud ends. Okay, we can try to now move these pinned particles to different positions, maybe on the Fermi surface, because that's where we should see correlations. But somehow we don't see anything. Okay, big disappointment. Not quite, because in this case the attraction was very, very weak. The attraction was not sufficient. But now what we can use, and you've seen this also in other talks, there's this BEC crossover and so on, BEC, BCS crossover. We can use our Feshbach resonance to make the attractions stronger, okay? And now we can try the same thing, pin the first particle somewhere, and now if we pin this close to the Fermi sphere, we see quite some enhanced probability to find a particle on the opposite side of the Fermi sphere, okay? And only if I go inside, there's no correlation, but if I go to the edge of the Fermi sphere, yes, there is, no? So now, we can try and check what happens if I make the attraction even stronger, okay? What happens then? You can see even far outside the Fermi sphere, I can already see momentum minus momentum correlations. I can see this on the Fermi sphere. I can see this also deep inside the Fermi sphere. Yeah. So now we have created molecules. Yeah. Now these particles are bound everywhere. The Fermi surface actually no longer really exists, but all the particles are bound into molecules. Yeah. Which are of course also correlated in momentum space. Okay. Yeah. And so now the question is really this, yeah, for this intermediate interaction strength here, we can see that correlations are predominantly present on the Fermi sphere. And our question is really, can we call this Cooper pair? Yeah? Can we call this the observation of Cooper pairs? Yeah? At least to our knowledge, we don't know that really this has ever been observed in such a direct way that one has actually pairs in momentum space, yeah, in this form, as a p minus p correlation. So we can try to do a little bit a comparison with BCS theory here, and what we can do and analyze from our data is how many pairs do we actually have in the system. Well, that's basically just take the integral over this p minus p correlation function and plot this as a function of interaction strength. And the unit of the interaction strength here, that's just the strength of the confinement in the radial direction. So I have to compare the internal energy, the motional energy of the system with the energy of the attraction, so to speak. Yeah. And what you notice, so this is a curve that you calculate for BCS theory, and well, we all know this. For any finite attraction, a Fermi gas should form a BCS state and form a paired system. Okay, that's exactly what is represented here. Very quickly, we should see a large number of pairs. Yeah, and that's not quite what we see in the experiment. First, we see basically no pairs, and then a relatively rapid increase compared to what we see in BCS theory. So should this worry us, or should is this actually something interesting? So we are working on understanding more theory on this. But in fact, it's even to be expected, because what we have here in our finite system, there is one energy scale that we, don't take into account in the BCS theory. That's the finite single particle gap that the system has. Yeah, that we ignore in BCS theory because we have a continuous system. Yeah, and that is actually causing the suppression here. And we had some previous work looking at the spectrum of the system in this regime, which where we could observe something like the emergence of a phase transition from few body physics, and that exactly happens in this range of interaction strength. So it's absolutely to be expected to observe something like this and to observe Cooper pairs somewhere only at some finite interaction strength. Okay, and that's really the energy scales that play a role here. You have the binding energy of two particles, you have the Fermi energy, and you have the trap spacing. And in our case now, for the very small system, the trap spacing and the Fermi energy, they are not very far apart. Yeah? And that gives somehow this rise of to these additional energies and additional physics that we see. Yeah? So this is, I'm at my end. I would like to tell you what the questions are that we are currently addressing, that we are interested in. Well, first of all, I think we would like to really understand, get some better theory insight. And there's a lot of work, like from mesoscopic physics, that we are like browsing through and trying to understand. We would like to get also in situ imaging, because I mean, you would want to see that basically you have no correlations in real space, but you have correlations in momentum space. That would be another signature that you really have Cooper pairs. Then, of course, it could be extremely interesting to find somehow correlations beyond second order. Maybe some ideas beyond the Pauli crystals would be very nice. Yeah. So I would be happy to discuss. Yeah. And then increase the particle numbers. We've been working on this. We can do maybe 50 particles. Yeah. It looks like. Then questions like at finite temperature in the normal phase, how pairing occurs. There's some old story that we've been following. And currently, and you can talk to Sandra about this, she's shown her poster yesterday, but I'm sure she's happy to show it to you again. We are looking at imbalance systems, so that's basically something like that. Yeah. So one impurity, that could be a polaron, or a few impurities. Imbalance, we could see maybe FFLO. And now I would like to thank you for your attention. And this is my team that did all the wonderful work. Dziękuję.
Dziękuję, Selim. Fantastic. Do we have some questions? Giacomo.
Very nice work. Thank you. I have a question, maybe general. When do you expect to see the transition? Of course, you change the binding energy, but when do you think for the particle that you can get inside your system, a transition between two body and many body? Because the pairing that you describe in the Cooper pairs is a many body, should be described by a many body effect, and the molecules is a two body effect. I'm correct? And when can you see the transition in number of particles that you can inject inside?
I think, I mean, to be honest, I think there is no real one transition. Yeah. So it's really these energy scales that you have here. Yeah. For the case of molecules, I think what you need to have is that your binding energy, if that you see real two particle effects, like two particle molecules, then your binding energy has to be much larger than the Fermi energy. That's that scale. Yeah. Then the many body physics is basically out. Yeah. And that of course can always be reached. Yeah, we just dial in more attraction. Yeah. But in our case, that's what I said. You know, there's not such a huge difference between, well, you know, factor of 2 or something like that. Yeah. Between the Fermi energy and the single particle gap. So this is somehow a little bit intertwined. Yeah. And now you can say, when does the transition happen? I think you just go deeper and deeper. The question is now, do you see a qualitative effect that comes from one or the other? Yeah. And so far, I'm not quite aware. I would be also interested to discuss. I mean, if someone has something, you know, that one could only see for a larger particle number, like for example, an order parameter. Yeah, that would be something like that. Yeah, I don't think we would see for the current system. I mean, we're talking about like there should be a phase transition, but I mean, then we would say a normal and superfluid. But I don't think that we would currently be able to see something like an order parameter there. So. Yeah, so that's one should call this maybe a precursor of a phase transition, something like that. Yeah, but otherwise, yeah, that would be one quantity that I would be very intrigued to see. Yeah.
Tomek.
Yeah, thank you. I have a question to the definition of the number of pairs you presented, because you, in this definition, you assumed a perfect matching of the momenta. of both. But maybe this is not exactly true in the mesoscopic system, and maybe you should try to integrate with some filtering function, which width depend on the interaction strength, and then maybe the matching to the theory would be better.
I think in this, so thanks for the comment. Yeah. So indeed, I mean that, you know, to get like the absolute values, one has to be take sometimes some of this with a little bit of grain of salt, but also, I mean, I think qualitatively, you expect exactly this suppression here. Yeah. Yeah. That's not a surprise. Yeah. You should see that. Yeah. That matches exactly all the other experiments we did. Yeah. And then that this overshoots here is also obvious, yeah, and that's only showing, you know, like relatively moderate attraction, yeah, because then you reach the molecular regime which is not captured in BCS theory, yeah. So qualitatively already not so bad, yeah, but I think we need to do really good theory to actually to be, you know, this is not claiming to making a quantitative comparison, yeah. This is, we should take this like as a very qualitative comparison indeed, yeah.
There is, I think, one talk in the one question in the chat. Thank you for a nice talk. In the two-particle correlation, where does the additional diagonal anticorrelations come from?
The two-particle correlations, probably he means, maybe you can unmute yourself and rephrase the question again, but I'm assuming that you are referring to this slide here.
Yes, that's true.
Yeah, and what do you say, the
So-
additional diagonal anticorrelations?
So you briefly talked about that you wouldn't find two fermions along the main diagonal, right?
Mhm.
But then you have additional diagonal.
So that the
move
additional
further
here.
up.
Yes.
I guess so. Yeah.
So that that is basically, I mean, if you want a an interference of the two-particle state, yeah, which comes just from the separation of the two wells. I mean, the two particles are released at a discrete distance from each other, yeah, and you can say this is like the two-particle analog of a double-slit experiment, if you want, yeah. And in the two-state system, this is then the interference, yeah, if you want.
Right,
Yeah?
yeah. Okay, makes sense. Okay, thank you.
Any more questions or comments? I have one comment. Last week we have been, some of us at least, listening to Marius talk, and after there was a discussion that maybe in some regime, if you have strong repulsive interaction, you can form an antiferromagnetic order by combining the Pauli crystallization in each of the species with the repulsion. This, of course, depends on the scales, as you say. So I don't know if it is really doable, but maybe one should look.
So in one dimension that works. We have done this in the past for one dimension. Yeah, that has worked. Yeah, and you can, this kind of, you have to work basically in this infinite repulsion limit. Yeah, and then across infinity you get like either antiferromagnetic or ferromagnetic correlations as being the ground state, and you can make, you know, you can have something like spin chain. Yeah, yeah. I'm not sure. I don't think that it actually works in 2D. Yeah, I don't think you can make the repulsion strong enough. Yeah, so infinite repulsion is not sufficient somehow, I think. Yeah, which is the case, you know, in 1D. You know, at infinite repulsion, you have a perfect spin chain. Yeah. Yeah.
I mean, that's why, in fact, in the discussion we were looking at Tillman and dipolar.
Yeah. Then, yeah, different story. Yeah.
Okay. Any more questions or comments? I don't see the case, so let's thank Selim.